Good morning to everyone. Last class we discussed about the what is orthogonal, what is the purpose of orthogonal matrices, and then what is the use of orthogonal matrices. Here we discuss some orthogonal basics. See, usually we know that the A transpose into A is equal to A into A transpose equal to I. That is orthogonal matrices. If it is matrix is orthogonal only, the possibility is A transpose into A into A transpose is equal to I. Then an orthogonal is a set of vectors that are mutually orthogonal and have unit length. So it is unit length, it will be a perpendicular. This type of basis is essential for representing representing the in a way that preserves distance and angles. See, distance and angles, we know that the distance between the two values, that x comma x1 comma y1, x2 comma y2, then it is the way to orthogonal matrices we have to finding the unit length. It is a even a mutually orthogonal, it is have the unit length. See, then the properties. Next we have to discuss some properties of orthogonal basics are convenient for performing calculations in vector space as they simplify dot product and projection. See, usually that the products of dot product and cross product in a vector field, that is the orthogonal matrices, it is convenient for performing calculations in vector space. That is the very important thing, that the calculation of vector space as they simplify the dot product, only is the dot product and the projections is a very important. Then the applications. See, in this orthogonal matrices there is a lot of applications, and then particularly it is the orthogonal base are used in the various applications include signal processing, data compressions. See, the signal processing, see, it's a very in this world we are going to a AI. So in this AI process, that including the signal processing, data compression and quantum mechanics. So these two is a very important to do that. So that is the application. And not only here, that in this application we are using the so many applications. So usually that A transpose into A is equal to I, that is identical matrices, it is called a 1 0 0 0 1 0 0 0 1. In this application of matrices, for example, the standard basic vectors are 1 0 0 0 1 0 0 0 1 in this 3-dimensional space from the orthogonal basis. So here that the orthogonal matrices that will be identical matrix, standard basic vectors are 1 0 0 0 1 0 0 0 1, that is the 3 dimensions space form and orthogonal basis. It's a very important thing. Then the diagram will be formatting in the vector field in 0 1 0 0 0 1 0 0 0 1. So in this 1 0 0 0 1 0 0 0 1 vector field is in the above form, it will be a form to the above diagram. So it is here R vector minus R naught vector, and then gen vector, then the R vector, that position vector, and then R naught vector. So in this 3-dimensional x, y, z, there are a space in a vector field. So R vector minus R naught vector, that is P to PO. Then the orthogonal transformations, that orthogonal transformations are linear transformation, and the linear transformation and the preserved distance and angles, they can be represented by orthogonal matrices. That is the rotation. The rotation in space transformation, the vector field, see the rotating it around an axis. So here the reflection, a reflection transforms a vector by flipping it across a plane. So the reflection transforms to the flipping it across a plane. Then the combining rotations and reflections can create more complex orthogonal transformations. So here the orthogonal transformation, it will be a linear transformation that preserves distance and angles. See, it will be a distance and angles. They can orthogonal matrices, they can be represented by the orthogonal matrices. So only is in this possible way the distance and angles to preserves, that is a only way to the orthogonal matrices. So in this orthogonal matrices will be doing that the rotations of in space transformation by the vector, it is rotating it around in axis. See, then the reflection, a reflection transforms a vector by flipping it across a plane, a reflection transforms. Then finally the position, then the combining rotations and reflections can create more complex numbers, and then the more orthogonal transformations. So in this orthogonal transformations using in the complex to create an effective reflections and the rotations. Thank you.